Hello, everyone, and thank you for joining this July meetup. My name is Denis Choucroun, and I am the program manager of the HP developer community. And today I'm very pleased to have Jade and Engin, principal software engineer and software engineer at HP, to talk about the vendor-neutral GPU programming in Chapel, a modern parallel programming language. And before handing over to Jade and Engin, I would like to give you a few housekeeping items about the HP developer community, as you might not be familiar with all the resources we offer for the community members. So, as you know, we have monthly webinars. We have two types of monthly webinars. The first one is called a meetup. Meetup is a sort of in-depth technology talk about any solutions, open source solutions, not only HP and product and solution, but also ISV partners, technical solution. The next session will take place end of August on the 28th, and this will be about fine-tuning for large language model. We have a second type of event or webinar called Munch and Learn. The Munch and Learn is a sort of thought leadership vendor product agnostic type of talk. And the next session will take place in the 18th of September, where we will talk about how to enhance NLP with RAG, the Retrieval Augmented Generation. We, as part of the HP developer community, we also have much more resources to offer to our members. We have what we call a workshops on demand catalog. A workshop on demand catalog is a set of hands-on labs based on Jupyter notebooks that are available to anyone and everyone for free all over the weeks and the months. So you can give it a try and provide your feedback, and you can leverage them to learn more about developer tools, utilities, solutions, and products. We also, as a community, welcome any contribution or any new members. So you can join our community through our monthly newsletter. So you can sign up to our monthly newsletters to be kept up to date about what's going on every month on the HP developer community. You can also participate to discussions on our dedicated Slack workspace for the HP developer community. You can follow on Twitter or X. And of course, as a community, we welcome any contribution through a blog post. So we have a link to help you get started on how to contribute and submit a blog post. You just need to have a GitHub account to submit a blog post. You can deliver a meetup or participate to an event or a meetup. Just reach out to us. And you can also work with us to add to our workshop on demand catalog a specific hands-on labs for a specific technology. Here you have a QR code that you can scan to get all the links about the developer community. So the portal is developer.hp.com. I will post a copy of all these links in the question and answer section of this webinar, so you can copy paste the links to join the community. Towards the end of this webinar, I will launch a poll or a kind of survey with 3 simple questions to get your feedback about this session. So with that, let's get started with the real topic today. And again, Jade, this is all yours. Thank you.
All right. Thank you so much, Deni, for the introduction, and thanks everybody for being here. My name is Engin Kayraklıoğlu. I'm a developer in the Chapel team at Hewlett Packard Enterprise, where I lead the GPU support efforts. And today I'm here with my colleague Jade Abraham to talk about vendor-neutral GPU programming in Chapel. So it's hard to avoid GPUs, and I will back that with some data from top 500. If you're not familiar with it, top 500 is a list that has 500 fastest supercomputers in the world. And what I will show you is a scatter plot, and y-axis will be the ranking of a system in top 500, and x-axis will be the different dates of the lists. And you can see like small slivers of green there. Those are systems that have GPUs, and the gray lines or chunks, if you will, are systems without GPUs. If you reveal the full plot, you can see the pattern that most of us are probably familiar with at this point, where you have a significant increase in systems with number of with GPUs. Specifically, we are seeing 13x more systems across these 12 years of period. And if you look at the distribution of these, for example, if you just focus on top 10, across these 12 years, only 41% of the systems have GPUs, whereas in the last 3 years, this number increased to 72%. And if you look at from a wider perspective, the increase in systems with GPUs is even more dramatical in top 100. So GPUs are becoming more common and they are easy to find, but they remain difficult to program. So if you look at the parallel programming landscape in general, for shared memory, we have OpenMP as the de facto standard almost. And then distributed memory, similarly, MPI dominates the field. But if you want to get good performance out of your application, you typically want to combine them, creating this new paradigm, almost MPI plus OpenMP. And this is not talking about GPUs so far. So if you want to do GPU programming, there's also a whole batch of different technologies. CUDA, HIP, and SQL are from vendors. There are other technologies that are not from vendors. OpenACC and OpenMP, again, are directive-based solutions. And we have also Raja and Cocos that are C++ templates. And what's really important at this point is if you look at this bubble of GPU programming technologies, there's no really distributed memory support here. So that implies that you still have to go back to MPI, creating applications that are based on MPI plus CUDA, or even something like MPI plus OpenMP plus something from this bubble. So all of these are effective, powerful, essential, and tested technologies. But at the same time, programming for multiple nodes that have GPUs appears to require at least 2 programming models. But maybe even more important than that, most of these, or all of these programming paradigms, if you will, build on top of C, C++, and Fortran. But these are not the languages that potential HPC users or parallel programming users learn in colleges. These potential users are scientists, data analysts, AI engineers, and whatnot. And they typically want to program in higher level things like Python, MATLAB, or maybe Julia. So as a result, using GPUs in HPC and maybe parallelism has a really high barrier of entry. And we believe that Chapel is an alternative for productive, distributed, and shared memory GPU programming in a vendor-neutral way. And today we'll be talking about that. So what is Chapel? Chapel is a modern parallel programming language. It's designed to be portable and scalable, and it's implemented in an open source and collaborative fashion. Our main goal is to support general parallel programming, not just HPC or not just GPUs. And we also want to make parallel programming at scale far more productive. And how does Chapel achieve all of that? First of all, Chapel works everywhere. You can develop on your laptop and have the exact same code scale on a supercomputer. You have the necessary tools to diagnose performance, would-be performance on a supercomputer, even using your own laptop. And you can target GPUs in a vendor-neutral way. You can use Linux laptops, clusters, Cray systems, macOS, Windows subsystem for Linux, AWS, Raspberry Pi even. And it's been shown to scale on Cray networks, InfiniBand, RDMA, Ethernet. And Chapel is not only portable, it also provides an easy interface for parallel programming, because parallelism is the first-class concept in Chapel, and everything in the language is built around parallelism. What does that mean? We have data parallel locality aware loops. We have the ability to move execution and allocation to remote nodes. And distributed arrays and bulk array operations are, again, first-class citizens in the language. And more importantly, different types of parallelism, as we will see in this talk, can be expressed with the same language features. So all of these nice features are powered by the fact that language is designed around it, compiler is designed around it, and the runtime is designed around it. And in terms of portability, today we are here to talk about GPUs specifically. Before we dive into that, I want to talk a little bit about Chapel applications. So these are some subset of applications that kind of on the more, I don't know, they have been developed for a longer period of time than just a personal side project, likely with multiple people, and they have been impactful in their fields. And some of them are really large, some of them are small in terms of code size. So for example, Champs, the one on the top left, has more than 100,000 lines of Chapel code. So it's a serious application with a lot of dependencies, with C libraries, et cetera, et cetera. And among these applications, we are aware that these 5 have active GPU efforts. And as a teaser of what's going on in our community, I will start with this one, rapid queue mapping crawl biodiversity. So let me start by trying to explain the application, because I'm not the scientist who implemented the application. This is a spectral biodiversity image analysis application. What does that mean? You have a satellite image of an island where you think there might be corals in the shores. And you have multiple images at different points in the light spectrum. So what you want to do is you look at those multiple images and create a heat map of biodiversity. And that heat map can point you to the locations where coral reefs might be. So you can maybe arrange like diving expeditions for further look, or you can establish protection zones and whatnot. So this is a pretty standard stencil application, although the numbers are relatively large. The satellite images in realistic sizes we are thinking about is like 15,000 by 15,000 at minimum. And then you run a stencil across this across these images, and stencil's radius is also relatively large, in a couple of hundreds. So this is a pretty arithmetically intense operation, and this was brought up by an oceanographer who was visiting our team, and this is simply an unapproachable problem, because what they did is like they did a back of the envelope calculations based on a CPU based solution to extrapolate what would it take to run realistic sizes on a laptop, and the numbers that they were getting like 27 days or something. So that's definitely not something that they can achieve on their laptop. As I said, they already implemented the CPU-based version and run it with smaller data sizes. This is a very kind of skeleton way of explaining the application. The whole thing works in the convolve function, as you can see on the top. It has a huge for loop that does ton of math, bunch of nested loops, et cetera, et cetera, et cetera. And the main function is just for input-output, where input is a 3-dimensional array in Chapel, and 3-dimensional because 1 dimension is just number of images, and then the output is 2-dimensional array, which is just a heat map of the area. So we took this application and we made it multi-node, multi-GPU, multi-thread parallel in relatively straightforward steps. And this is the structure after making those changes. So first of all, we use a different loop flavor. As I said, parallelism is a first-class concept in Chapel, and we have different kinds of loop flavors, and some of them have different implications on parallelism. So for each is one, and it enables GPU execution. The next step is this chunk where you see 3 co-for-all loops. Co-for-all loops are yet another loop flavor, and Jade will talk about them in their demo in more detail. But what this chunk does is the first co-for-all is doing multi-node parallelism, and then the second for-all is doing multi-GPU parallelism within each particular node, and the last co-for-all is doing multi-thread parallelism within each GPU. And that multi-thread parallelism enables communication and computation overlap. So with these 3 almost identical co-for-all loops, you can use many different kinds of parallelism in your application. And furthermore, if you have something like this that does multi-node, multi-GPU, multi-thread parallelism, you inevitably have to divide your input and output somehow. And that's also achieved by bulk array operations in Chapel. Namely, we can slice a multidimensional array to create a single worker's input, and you can copy that into a slice of a global output array as it's happening here. So all of these are standard Chapel features. If your array happen to be on the GPU, it's just a GPU to CPU transfer, or host to device, or device to host transfer, and vice versa. All of these are handled under the hood by a Chapel compiler and the runtime, thanks to those being first-class citizens in the language. So what about performance? We can run this on Frontier after these straightforward changes, and we are seeing 5x improvement going from 2 to 64 nodes. So if you ever done scalability studies, you can already tell that this is not like an outstanding number, 5x improvement up to 64 nodes. But this was our very first real application where we were running multi-node, multi-GPU, multi-thread parallelism. But maybe more important than that, remember that 27-day figure that we were calculating that this would take? At 64 nodes, this was just taking 20 minutes. So this now became an approachable problem for the scientists. So this was really an exciting observation for us. And the lines of code in this application is like 300 or something. So it's a relatively bite-sized application that does all that science and all that parallelism. All right, so with that, what we will discuss today. So I will give a brief overview of parallelism and locality concepts in Chapel at a very high level. And then I will hand it over to Jade, where Jade will give a live demo on these capabilities. And then we will wrap up with some stories from the Chapel community. Let me jump right in. So GPU programming in Chapel revolves around this concept of locale. So locale is another first-class concept in Chapel, and I will try to explain what that is right now. So in a supercomputer allocation, or a cluster allocation, if you will, this is kind of a typical scheme that you have, where you have multiple compute nodes available to your application. And each of these compute nodes have some number of processor cores and some amount of memory. And these nodes are typically connected on an interconnection network, as you can see with the green lines here. So in Chapel, what we have is this concept of locale. And locale refers to a compute resource that has processors and memory. So namely, for the context here, you can just think of each compute node as a locale. So with that definition out of the way, now our diagram looks like this, where we don't call them compute nodes anymore, but locales. So how do we support this idea of locale? It's not just terminology. So first of all, we have this type called locale in Chapel. This is just as int, real, string, bool. This is just a built-in type in Chapel that represents the compute node that you're running on. To further support locale type, we have locales array that is predefined for you, and that's an array of locale values. So if you have 4 compute nodes allocated to you, then you have a Chapel array named locales that have 4 locales in it. Last but not least, we have here. Here is another built-in variable that tells you which locale the current task is executing. So as you can see by the turning cog on locale 1, if that's where your application is running right now, just querying here will give you locale 1. So these are key concepts that supports the idea of locale in Chapel, which will be crucial in GPU programming. But taking a step back, what are key concerns for scalable parallel computing? First is obviously parallelism. Do you want a particular task to run sequentially or in parallel? So a sequential run would look like this, or if you want to run it on parallel, it would just execute on all cores. But there's also another concern, and that is locality. Where do you want this task to run? Or almost analogously, where do you want your data to be allocated? So you might want to run on a single locale, as you can see on the diagram here. You might want it to run across locales. And if you combine the concerns of locality and parallelism that are almost orthogonal, you can think about running on all cores. And very similarly for data, you might want to allocate your data on locale 0, or you want to distribute it maybe, or maybe you just want to replicate it. So all of these combinations of where the tasks run, which are parallel, and where the data is allocated are all the combinations are really valid combinations. There's not a silver bullet that can fix all the applications, right? So based on your use case, as a programmer, you just have to pick the correct combination for your application. And the key point here is that your language should allow you to do that. So far, so good, but we have not talked about GPUs. So GPUs complicate the matters a little bit because they also have their own processors and their own memory. So if you think about the definition of a locale, they look like a locale in themselves, right? But they also happen to be inside compute nodes. So that's also an important information that you cannot just ignore. So how we represent GPUs in Chapel is by the idea of sublocales. So with the introduction of GPUs, what we currently have is each locale also has a sublocale or an array of sublocales, if you will, that represent GPUs. So what comes next is Jade's demo, where they will talk about the concept of sublocale in the context of code. And Jade, if you're ready, I can relinquish my screen share.
Yep. Okay. So this is some simple Chapel code, and we're going to go through some examples on two different types of machines. So this first one is a single node with a single AMD GPU. And then we're going to take the exact same code and go run it on a a one node with 4 NVIDIA GPUs. So starting out here, I'm just going to walk through some of this Chapel code. This is not a Chapel tutorial, so we're just going to talk at a very high level about some of these concepts. A couple of important things here. These config constants are going to let us control how the program runs from the command line. This all gets handled automatically for us by the compiler. Kind of the most important part here is which compute node we're going to compute on. So we're going to query our current locale and then look at all of the sublocales that it has. And if we have any sublocales, then we can use the first sublocale here. So that first sublocale will be our target locale. And if we don't have any sublocales, we'll just use the here. So in a much higher level, this is either using a GPU or using the CPU. We can then use that target locale and declare our array on the target locale. So now if target locale is a GPU, we have declared array in GPU memory, and otherwise we've just declared it on the CPU. We can then move computation to where that array is declared and start executing kernels. So there's a number of different ways we can execute kernels, but I think it's more fun to just see it happen in real time. So I've compiled this for an AMD GPU already. And if I run it with verbose GPU and print, we can see what happens. So we'll see, first of all, there's a kernel launch on line 21. And if I go to line 21, that's this parallel loop over the elements in the array, and we're just assigning the elements to the array. There's then another kernel launch on line 25. And this does not look like a loop or a kernel of any kind, but what's happening under the hood is the Chapel compiler is turning this nice array syntax into a parallel loop that is then GPU eligible to be launched as a kernel. So this program has 2 kernel launches, and then of course we can dump out all of their values. It's not very interesting because we're just initializing and incrementing. And of course, we can adjust the size of this problem and print lots more numbers. But let's go look at a slightly more interesting example, which has a very similar structure. But now when we're selecting GPUs, we're not just going to select a single target locale. We're going to select a target locale which has multiple. So we have an array of locales. And so here we're either going to use all of the GPUs that are available to us, or we are going to use as many of the current CPU as we can. So the number of locales is going to be equal to the number of CPUs. And this isn't really necessary to get parallel CPUs, but it does make our code a little bit more concise when we're trying to target both CPUs and GPUs. So our target locales is either our GPUs or CPUs. And we can then declare our array on the CPU. And then we get into those coveralls that Engin was talking about. So what this code for all is going to do is for each iteration of this loop, so for however many chunks there are, it is going to create a task and do something in parallel. So if n chunks is 10, each iteration of this loop, which will be 10, will happen at the same time. And then in each iteration of the loop, we'll go to the current target locale that we want to look at, and we will get a chunk of memory, and we'll do an increment on it. So this is kind of a very low-level way to initialize each segment of our array, our host array, to be essentially the number of the locale. So either the ID of the GPU or the ID of the current task that we're on. So if I run this program, and I'm going to run the CPU version first, which all I need to do to get a CPU version of this program is recompile with a different flag. And if I just print it out, you'll see that the numbers go up to 64 because there's 64 cores on this machine. And if I run with verbose GPU, nothing extra is going to print because we didn't run this with any GPUs. So now I can switch to using the GPU on this system. And if I just do a print, see, it's not the most interesting output because, again, there's only one GPU on this system, but we can confirm that, GPUs are doing something with verbose GPU. We can see this copy from host to device on line 28, right? So we're taking our host array, we're copying it into device memory, we're doing our computation, and we're copying it back. So let's go ahead and switch to a little bit more interesting example on a node on AWS with 4 GPUs. So give me 1 second. Awesome. Okay. So like I said, the exact same code, but now it's been compiled for NVIDIA with 4 GPUs. So if I run this exact same example, except you can see now the file name has NVIDIA in it because I've compiled it for NVIDIA. And I run it with verbose GPU and print. So now there's a lot more kernel launches happening, and we can see that the ID has gone up to 4 because there's 4 GPUs. And if we look here at all these different kernel launches, individually, there's still that same host to device launch and device to host transfer. But over here, we can see exactly which GPU is doing the work. And so we've now got 4 GPUs doing the work. So let's take a slightly more interesting example that uses pretty much this exact same code, and all we're going to swap out is this internal section here. So if you're not familiar with it, a sigmoid function is commonly used in AI to do activation within a neural network. So we're just going to initialize the array, get some interesting stuff out of it. And then if you're not familiar, this is what the sigmoid function is. So for each element of our array, we're going to do this computation. And we can write this in very succinct chapel code, no loops required, just kind of writing, we're doing our computation on the device array and assigning back into the device array, and then copying back to the host. So this here will get turned into a loop, which will then become a single GPU kernel. And of course, if we don't have GPUs, it will still be a parallel loop. It's just not going to be run on the GPU. So we'll see that in action on file. So there's our CPU version, and we'll print it out. And we'll run the GPU version as well. And so again, we have our kernel launches coming from something that just does not look like a loop at all, but this is the full computation. And really just to drive this home, we're going to go to another example that is very similar to this, but we're actually going to add a little bit of extra work before this kind of same loop. And so again, this is softmax, which is also used in AI in neural networks. And the definition of softmax is this expression right here. So for each element in our vector, we are going to take it to the natural log, or natural exponent, and then we're going to divide by a sum over all of the elements in the array. So now we need to do a reduction of the array. And so like before, we have this code for all. This is the same code as before, and we're writing our expression here. But now we have this exp sum that we need to compute. And we'll go ahead and look at how that's defined. So in the simple CPU case, or for a single GPU, this is one line of code. And we can write plus reduce and then exp post array. This right here is a parallel operation that will not only expand out this expression, but also do a reduction over all of the elements. And on the CPU, this works. And on a single GPU, this will work. But we want to use as many GPUs as we have in our system. So you'll see that familiar code for all to create essentially one iteration per GPU. And then we'll move the computation to that GPU and do the computation like before, getting our device array and doing plus reduce. The interesting thing here that makes this kind of chapel-tastic is I've got this intent here. So I am expressing my intentions to the compiler with a plus reduce intent. And what I'm saying is this exp sum is going to be summed in this loop. And so by telling the compiler this, I can help it optimize and get better parallel code. So I not only tell it what my intent is, but in a single expression, I get my kernel launch. And then we have our exp sum to then come down here and do our same computation as before. So let's go ahead and run this. And it's going to take a little bit longer, but let's run it with verbose GPU so we can actually see what happens. And of course, print it out. So now we've got a lot more kernel launches going on, and I'll just make this bigger to see what's happening. So again, per GPU, there's 4 GPUs. So everything is duplicated 4 times. And there's this kernel launch on line 40, which is that GPU reduction. And there's also the kernel launch here, which is using the result of that reduction to compute. And while I'm here, I'm going to show one other useful feature. So say you're developing your application on a laptop that doesn't have GPUs, but you want to write code for GPUs. I've also compiled this code for GPU, and we call it CPU. So GPU, CPU. This is CPU as device, and we're going to basically pretend that our CPU looks like a GPU. And if I run with verbose GPU, you see we still get the kernel launches, and there's only one of them because we're just emulating one of them. But this kind of feature helps if you have a laptop that doesn't have GPUs, but you want to develop your application to work with GPUs. So that's just a nice kind of portability feature of Chapel. So the last example that I'm going to show here is much more involved. It is a GPU implementation in Chapel of Conway's Game of Life. So if you're not familiar with Conway's Game of Life, I have the rules right here. So we have a 2D cell of a 2D grid of individual cells. And each cell has some rules that determine whether or not it lives or dies and survives to the next generation. And so any live cell, so in our code example, it's going to be a Boolean value of true is live. With fewer than 2 neighbors is going to die. If it's got 2 or 3 live neighbors, it will live. If it's got more than 3 live neighbors, it dies. And then we can also bring dead cells back to life if it has exactly 3 live neighbors. And this Conway's rule of life is codified into Chapel right here. So again, we can use Chapel's 2D arrays to figure out how many neighbors we have, and then we can check, do we have 3, do we have 2, and what is the value of our current index in the grid, and then we can compute the next grid. So this is a single iteration across our 2D array. And if we come up to our code, we'll see that that gets run inside of a parallel loop that is going to become a GPU kernel. Before I talk about this loop a little bit, we're going to talk about the head of the loop here, where I'm not only, right, so this code is only going to use a single GPU, just kind of for simplicity of the example. Of course, you could write it to work with multiple GPUs. So we're going to just select our target locale, either the CPU or the GPU. We'll declare domains for our arrays. So we're going to basically set up how we want to index our domains. And the reason this is how we want to set up our arrays. The reason this is useful is because we can define our arrays over this slightly larger domain, and then we don't have to worry about bounds checking when we're running our kernel. So if you've ever worked with GPUs, if statements are really bad, we don't want to do that. And so this allows us to really nicely avoid any kind of bounds checking work. So we've declared on the target locale our two arrays. We'll initialize it to some random state, and then we'll move computation to that target locale. And now we can go ahead and talk about the kernel. And there's actually two kernels here. So there's not only this kernel here, which is going to run this function for each iteration on the GPU, but we also want to check if kind of there's nothing more happening and everything kind of stabilized and settled down. And then afterwards, we're going to use this result in another kernel launch to reduce that array and check if we're stable or not. And lastly, we can just kind of swap in a constant time operation these two GPUs for the next iteration. So under the hood, this is like a pointer swap. So there's not a lot of copying back and forth overhead. So let's go ahead and run this. And I'll run it without the printing first, just to show the GPU communication alone. And we're running it with kind of a small image and only 10 generations, but we'll bump that number up in just a moment. So running it with verbose GPU, there's all the kernel launches, and we can go jump to that code there. There's the first kernel launch. There's the second one, and you can see that happens a bunch of times in a row. But this isn't maybe very interesting to look at. Yay, we can see GPU communication. Let's see a cool video of it. So I'm going to go ahead and bump up the image size. Just make sure I get my syntax right here. And we'll bump up the number of generations this is going to run. We'll just run it with 100. And we need to run it with print. And we'll let that run. So you'll see while it's running, we've got all this GPU communication that's happening. But now, I'll just stop that scrolling for a second. You'll see this extra kind of copy back from the device to the host. So before, all of our computation was happening in GPU memory. But now we're going to copy information from the device back to the host to be able to print it out. And maybe this will be almost done. There we go. And I can go ahead and open up that video, and we can see the result of what our GPU computation was. So there is Conway's Game of Life, just a short little segment. And again, this was all running on the GPU and just kind of moved back to the CPU to create this pretty image. And with that, I'm going to hand it back to Engin to talk more about some of our Chapel community.
Jade, yeah, Dennis,
we have a
please
question about your demo.
Yeah.
Your question answer.
So Jade, the question is, in the softmax example, it seems like you are initializing exp sum before it is being used. I was wondering why it does not cause an error.
So exp sum is set up here. And then it is computed here, and then it is used down here. That may just have been the order that I showed it in, but it is, declared up here and then used down here.
Thanks, Jade. I also see another question in the chat about profilers and debuggers for GPU support. I'll quickly answer that before we go on, and then we can do follow-ups at the end of the talk. So for profiling and debugging, we have experience using Nsight Compute to profile CUDA kernels, and similarly CUDA GDB to debug them. We generate PTX, so anything that you can use with a PTX can be used. In general, profiling a system is a bit more challenging because of Chapel's threading library, QThreads, which is a user-level threading library that profilers have some difficulty understanding. But that's not about GPUs. It's more about like if you want to profile a supercomputers run with multi-threads and etc. I'd be happy to answer any follow-up questions, but for now, I think I will move on, if that's all right. So thanks a lot, Jade, for this amazing demo, and it will be really hard for me to follow that with just slides, but really great job. And if you're interested in taking a look at the code, it's available right now on GitHub. You can scan the QR code, and the slides will be available, so you can check it after the talk as well. Now let me go on with some stories from the Chapel community real quickly to see what our community has been doing with GPU support. First, I will call out a paper that was recently presented at IPDPS, Heterogeneity in Computing Workshop. And this is a paper that compares Chapel's performance against OpenMP, Cocos, CUDA, and HIP using different GPUs and CPUs. Using benchmarks Babel3, Minibuild, and TLeaf. If you're not familiar with those, they are from University of Bristol's HPC group. And papers available, again, link is on this slide. So I will just show results from Minibuild and only subset of it. Minibuild is a proxy for build, which is a protein docking simulation. So this is a very arithmetically intensive application with a lot of trigonometric functions. The tables are a screenshot from the paper and kind of crowded, and we will not go over them in detail, but roughly left and right hand side are showing pretty much the same thing. One is raw data, one is ratio, if you will. And each table has CPUs and GPUs on the y-axis. Top 6 or 7 are CPUs, bottom 5 are GPUs. So they're similar across both tables. And on the x-axis, you have different technologies, including Chapel. So with all that, I want you to focus on only this quadrant, which is just GPUs and ratios. As you can see, Chapel is comparable with CUDA on NVIDIA devices and comparable with HIP on AMD devices. This paper has 2 other results. One is also similar, one where we lag behind. We are working on that. So that's kind of full disclosure. If you want to learn more about it, please check out the paper. The next paper that I will call out is more at scale. That was just a single GPU performance. So this one compares Chapel's native GPU programming to interoperability. So Chapel has really strong C interoperability support. So you can call a C function that can in turn launch a HIP or CUDA kernel. So that's another way of using GPUs via Chapel, but it's not what we have been discussing today. So this is a paper that compares the native GPU programming, which is the topic of today, to interoperability using Frontier and Perlmutter. If you're not familiar, Frontier is an AMD-based supercomputer and Perlmutter is an NVIDIA-based one. Frontier is the fastest in the world. Perlmutter was 12th last time I checked. So they are really big supercomputers. And this is a combinatorial optimization research, and it uses N-Queen's problem as a proxy. This paper has been accepted but not presented yet. So if you're in Europar in Madrid, Spain, late August, I recommend go check it out. So this is the results from the paper, which is again a little bit of a crowded plot. But what we can see here is with large data sizes and with small data sizes, native and interoperability versions behave pretty much similarly, where maybe the native version is just a couple of percentage points behind interoperability version. One thing that I will call out here is that the left plot is on Perlmutter and the right plot is on Frontier. And you'll see that there's some missing data on the right-hand side. That's large data size using HIP and HIP and Chapel. And the reason that the data is missing is because we had some seg faults in our HIP reference. So this is probably a fault on the on our side, that we made something wrong on the HIP implementation, but Chapel code was running fine. So this is also another testament of importance of portable code, because you write code on one system and it works on there. You can use the same code on different systems and it will work there as well. So that's the case that we were seeing here. Chapel was working everywhere, but we were not able to get the HIP version running because we make errors, right, as programmers. Last but not least, I want to call out ChapelCon 24's keynote, which was given by Paul Sapri, and it was a really amazing talk. It's not strictly just about GPUs, but Paul is one of the earliest adopters of Chapel's GPU support and has more than a decade of experience programming GPUs. And this is more about importance of parallel first languages, as we have been talking about in this talk. So I strongly recommend you check it out. The link takes you to abstract slides and videos that are available on YouTube as well. Let's wrap up. So where we are today is that we've been working on implementing Chapel's GPU support over the last 3 years, and we have support for NVIDIA and AMD GPUs pretty symmetrically right now. We can use multiple nodes, multiple GPUs, multiple threads in conjunction or in combination. We also have this mode called CPU as device, as Jade briefly alluded to, where you can use GPU features on CPUs. So this further supports Chapel's portability, where you can develop on your laptop and put your code on a supercomputer. That being said, you can see the code volume evolution that is pretty much linear, and that means we are still adding big chunks of implementation. We still have, we are still working on distributed array support with GPUs, which would make programming GPUs much easier on multi-node systems. Intel support is not something that we have been able to prioritize so far. And we are also working on improving existing language features to support GPU programming and typical performance improvement and bug fixes. We also have active efforts going on the AI ML front. We have a Chapel-based tensor library already available on GitHub. It has PyTorch-like interface, and it's under active development right now. If you're familiar with LLM.C, which has been something recent, it's a GPT-2 implementation in C. We have its Chapel port, and we want to open source it. The implementation is there. We are currently working on the political path of open sourcing it. And we are actively looking into MLPerf and porting some of the benchmarks to Chapel. If you're interested in any one of those, please reach out. We really like you to contribute. And if you want to learn more about GPU programming in Chapel, we have blog series. We have a tech note that is more like a reference, and some list of talks are on the slide as well, where the very last one is kind of different than what we have done here, and it focuses on Chapel compiler's implementation of GPU support. So if you're interested in that, I recommend you go check it out. Chapel is open source. We would like to see you get involved, as I mentioned. So you can check out our GPU support issues if you want to contribute or just report bugs. You can join our Discord or Gitter channels to join the discussion. And last but not least, on the right-hand side, you are seeing the GitHub code spaces, which is kind of a recent effort from the Chapel team, where you can just click on a couple of things to get started on Chapel using GitHub and VS Code on your browser, which is a really nice tool to try Chapel. It doesn't currently have GPU support, but it's something that we are working on. All other resources on Chapel are on this slide as well, including social media, all our discussion channels, blog, and the webpage. So closing thoughts. GPUs are becoming more common, but programming them isn't really getting any easier. We cannot start with C, C++, Fortran, and expect Python programmers to start doing parallel programming. And GPU capability and parallelism are always like an additional framework on top of C, C++, Fortran, which is another learning curve. But we really want parallel programming GPUs and HPC to be more accessible. We believe that there are many potential use cases in different fields, including social sciences. And making GPUs and parallel programming in general more accessible accelerates humankind's progress. And Chapel makes parallel programming GPUs and HPC more accessible. Our existing applications prove that that's the case, and our GPU support makes Chapel an all-inclusive solution for parallel programming. With that, that concludes our talk and demo. Now we can answer any questions. Thank you so much for being here.
Thank you very much, Engin and Jade. I have just launched a end of session poll for attendees to respond to collect their feedback. Thank you again for all this invaluable information about Chapel. I don't know if, yeah, there is one question in the Q&A.
I am seeing, is GH already supported? Where GH is Grasshopper, I'm thinking. If that's the case, we don't have any experience on GH, on Grasshopper so far. Yeah, that's the best answer that I can give. One thing that I can kind of, it's a little bit of a speculation, but we have this mode that is called unified memory mode. It's a memory strategy specifically. So it's more for architectures like Grasshopper and maybe MI300. So we believe that that mode can be useful. It's not on by default right now because it's bad in terms of performance on more traditional hardware. So we believe that that mode will be more prevalent in architectures like Grasshopper and MI300. But as I said, we couldn't get our hands on Grasshopper to test extensively at this point.
Okay, any other questions? For the moment, no. Oh, yes. There is one more.
The question reads, what's the best way to set up a GPU cluster from the hardware perspective? I really don't know the answer to that question. I never really built one myself, especially from hardware perspective. I'm sorry if anyone wants to chime in. Jade, I don't know if you have an answer, but I'm seeing a head shake. Sorry about that. I'm seeing another question, FPGA support for version 3.x. Yeah, that would be an interesting question to think about. And FPGAs have always been scary to me, so I don't know. I don't have anything specific to say, but yeah, that would be an interesting thing to explore. Not something that we are actively thinking about, though.
There is another new one.
Yeah, the question reads, how can Chapel be used to implement distributed deep learning training and inference? So that's a really good question. And that's something that I can, again, speculate a little bit about. So I was the one who implemented LLM.Chapel, as I was mentioning. So LLM.C was a GPT-2 implementation in C. And it's about fine-tuning a pre-trained network in C and using OpenMP to some extent. So in my experience, in my limited experience in AI ML realm, using LLM.C as the reference, I saw that multidimensional arrays are key points here, and being able to distribute them so that you can use more memory is another key thing there. So Chapel has everything needed to support an application like that. And in fact, like porting LLM.Chapel was really relatively easy on the side of multidimensional arrays. So if you have like tensors, they are called like 5-dimensional arrays, 4-dimensional arrays, Chapel support them out of the box. So you can just have multidimensional arrays to be more expressive, to allow more expressive programming for your deep learning application. And you can have multidimensional distributed arrays. The key part that we haven't really covered in this talk is you can change your multidimensional local array to be a distributed one without touching your algorithm at all. So we have some examples of that in Chapel where you just change the arrays declaration and it makes it a distributed array, and then you can just keep using it. So I think that approach to multidimensional arrays and distributed programming can really enable much expressive and productive deep learning training and inference for the programmers.
Okay, so with that, there is no additional questions. So again, thank you very much for everyone for this, to attend this meetup, and thank you very much, Jade and Engin, for delivering this great session.
Thanks for the invite, Denny, and thanks everyone for being here.
Thanks for having us.